Welcome everybody. This is the outline of the talk. I hope I will be able to do it. Otherwise, I will continue tomorrow. It deals with classification of elementary particles and then how electron hadron families are filled. And in order to understand family structures, we need to develop internal symmetries. As these symmetries involve group theoretical treatment mathematically, I have put some extra sheet to remind you that our students already know group theory, particularly if they have done schooling and, of course, and also Anglo-momentum algebra. So with that, we will move on to fundamental forces and finally the standard model. So this is where we left yesterday. These are the broad classification of elementary particles. We all know that elementary particles often either are fermions or are bosons. So what we see here is that we can categorize them in two parts, that is matter particle, which essentially constitutes the matter, and quanta of forces which are exchanged between the matter particles in order to participate in electromagnetic, weak, strong, and probably gravity. So matter particles are divided in two categories, that is hadrons and leptons. Leptons are luckily 6 in number and they are point-like. They are not composed of anything else up to the present scale of energy. Whereas hadron families can be divided in 2 or 3 even categories. That is mesons, baryons. If you like, you can also add antibaryons, because from Dirac equation or relativistic treatment of fields, we have understood that every particle should have its anti-partner. So with this mesons and baryons, as I mentioned yesterday, we have very large number of them, several hundred, and there are reasons to believe that they are not point-like, they are not the fundamental particle. So they are made up of another layer, and that layer is of quarks. So this idea came around 1962, and onward we have 6 quarks. So there is an interesting similarity between quarks and leptons. Both are 6 number. These quarks, up, down, charm, change, top, bottom, or truth, beauty, we call them by these uh, names as flavors. So we will see more about this, that these can be divided in three family. First family made up of UD, up down quark, and electron and its neutral partner. Similarly, the second family, charm quark, stage quark, muon and its partner, neutrino partner. And third family, top, bottom, and tau quark, tau lepton and its associated partner and neutrino. So we will continue with this. So let me first remind you how these particles and when they were discovered. So I will be dealing with the major discoveries of elementary particle, and the story starts somewhere around 1895, when we identified that X-rays and gamma rays, they have typical particle-like behaviors. All electromagnetic waves, light waves, are associated with the corresponding photons. And this was observed by Röntgen. Then in 1897, I may be wrong about the figure. I hope these figures are all right. J.J. Thomson discovered electron. Then Rutherford probed the structure of nucleus and discovered proton as a most important constituent. In fact, the number of protons in a nuclei gives its atomic number. when it is surrounded by corresponding number of electrons, we have atoms. But he also suggested that there are reasons that we must have another neutral partner a proton. You know that proton carry positive charge. So he suggested it around the same time, but it was observed a bit late, after 10 years or so, by his student Chadwick. And then theoretically, up to now, experimentals were taking the lead. Then around 1927, Dirac synthesized quantum mechanics with special theory of relativity. Before that, you all know that we were using Schrödinger equation to describe, say, electrons inside the atom, and even protons and neutrons inside the nucleus. But we know that relativistic theory is better. They are accurately for all. They work accurately for all speeds. So when Dirac developed relativistic quantum mechanics, it's one of the very important prediction came out to be that every particle should have antiparticle. So in that way, he predicted that corresponding to electron, we have a particle with the same mass but whose charge is positive. That is called positron. Incidentally, around the same time, it was observed by Anderson at California Institute of Technology, US. And incidentally, Anderson was not aware of the prediction of Dirac, but it was an interesting coincidence that both theoretical and experimental events took place quite by. Then in 1937, suddenly muon was observed. Nobody expected it. Nobody really required it. Even now, it is a little bit puzzling. Why should we have muon? You know, is a heavy brother of electron. Its behavior is very much the same as electron, but its mass is large, and of course, it is unstable, and it decays to electron through weak decays. In fact, there's an interesting anecdote associated with it. Rabbi, who was an Israeli Nobel laureate, was sitting in a hotel when he heard this news, and he immediately snapped back, ordered it. Nobody needed, but it is there, and now we know even a heavy partner of muon is also there. That is called tau lepton. But points were genuinely predicted by Yukawa around 1935 because he wanted to explain short-range nature of nuclear forces, resulting as an exchange of three kind of mesons: pi plus, pi zero, pi minus. Uh, Historically, if you look at old books, both muon and pion were called mesons, but we have to be very clear about it. Muon belongs to lepton family, whereas pion belongs to the meson family. So it was observed a bit late, around 1947, by Powell. And then when accelerators came on the scene and cosmic rays studies were made more seriously, around 1947, the first strange particle was observed by Ruster and Butler. That is named Kaon. It's like heavy partner of iron. Then around 1955, antiproton was observed by this team of Chamberlain, Segre, Wiegand, and fourth person. And this antiproton is supposed to be antiparticle of proton. It was created in collision experiment. Then, as we all know, in order to save conservation laws, particularly conservation of energy, momentum, and angular momentum, Pauli introduced the concept of neutrino. Just a quick reminder. Initially, when beta decay was observed, you know that basically in this beta decay, atomic number of the nuclei changes from Z to Z plus 1 with the emission of electron. And it is a small exercise to my young friends to convince themselves just using classical energy momentum conservation. It is very easy to see that if neutron decays only to two bodies, that is proton and electron, then electron energy as well as proton energy must be fixed. It is a small exercise, and please do it. That you can show that momenta of the electron emitted is expressible in terms of mass of neutron, mass of proton, and mass of electron, which are known to us very well. So energy of the electrons emitted in a beta decay, if it is a two-body decay, should be fixed. However, we all know it's a now textbook material that in beta decay we have spectrum of energy. We don't have fixed energy of the electron. So in fact, at that time, even great people like Bohr were even puzzling. Maybe the energy momentum conservation may not hold for microscopic physics. But Pauli, because of his staunch faith in these mysteries of nature, and probably in somewhere in bachelor graduate studies, students must have seen the connection between space-time mysteries and energy momentum conservation law. Momentum is conserved as a consequence of translational invariance or homogeneity of space. In the same way, energy is conserved as a consequence of homogeneity of time, and angular momentum are conserved uh, is conserved as a consequence of isotropy of space. So this is now again a textbook level things somewhere in BSc one, if not earlier, all of us studied. So Pauli, because of his faith that space-time structure should not be broken, and we should honor these symmetries. So corresponding laws must be respected. So he then suggested that along with electron, another neutral particle, which is almost massless, should be emitted, and that restore all the three conservation laws. But he smilingly said, "I have given a problem to experimentalists, which they may not be able to solve." May not be able to discover soon, but the young ones are always energetic. Linus and Coleman, they suggested in nuclear reactor experiment that we can perform it and people welcome it. And in 1956, they finally confirmed the existence of a neutrino in the inverse decay. So with this, we go to another shade. Here again, I continue with the major discovery. The difference is the previous one could be handled by one person or a small team, but very soon as high energies were achieved, people had to develop big labs with a big team of scientists as well as technocrats, engineers, and all that supporting staff. And so all of the high energy experiments were carried on in these big labs. For example, in 1969, the first evidence of quark was obtained in deep in inelastic lepton hadron scattering. More precisely, when very high energy electrons were collided with, say, nucleons, protons, it is very easy to achieve proton. Just take water or take hydrogen, ionize it, and accelerating electrons to GeV level, they will have a de Broglie wavelength of the order of Fermi scale or even less. So that is how quarks were, were observed. Of course, it is an indirect confirmation. But the idea of quark was given by Gell-Mann and Zweig independently around 1962 in order to explain certain symmetry pattern of the hadrons. So this is really a great event because even Gell-Mann in his own paper of 1962, which has appeared in physical letters, he seemed to be little hesitant. He says, who knows they are physical, who knows they may be mathematical objects. But this nicely explained the structure, and today we have full faith that quarks are there as the major holder of the whole nucleus. And so that way the whole matter which we see around is coming essentially from quarks. But how many quarks? That is an important question because in 1974, this was a very typical year for high energy physics. lots of experiments were conducted around that time. And we have very rich time at that time, giving us lots of information about particle physics. So they observed a very unique kind of a particle, which is called J-psi particle, which require existence of a new kind of quark, that is charm quark. And in fact, it was already proposed by Bjorken and Glashow in around 1970, even little bit earlier, around 1964. And so this gave us a good boost that we are on the right track. And why do we have two symbols for this particle? Because they were observed in different labs, at SLAC and at Brookhaven National Lab. So that is why, to honor those efforts, they were almost contemporary, same time experiments were done and observation was made. One called it, the other called it, so we carry both the name. Then within a year, tau lepton was observed by Parallel at SLAC and Lawrence Berkeley Lab. And then in 1975, another particle, upsilon, which is heavy brother of psi, was observed, and there were indirect proposal by Kobayashi Mashikawa, who got a Nobel Prize later on. Around 1973, they suggested that if we want to have CP violation, this is a very important area of even today, then we must have a minimum 6 kind of quarks. So of course, now we know there are 6 quarks, kind of quarks. So this upsilon is made up of bottom and anti-bottom quark, like psi particle is made up of charm, anti-charm particle. Then at Daisy, Germany, gluon were observed indirectly as a 3-jet events. And then 1983, W and Z boson. These are the quanta of weak force, as you can see from the first sheet. And it was predicted by Glashow, Salam and Weinberg that if electroweak theories are to be described through quantum relativistic quantum field theory, then we have quanta associated with quanta of the weak force. And this prediction of 1967 was confirmed around 1983 by Carlo Rubbia and Meyer at CERN. And of course, their mass is quite heavy, so it took a little time to really create them. And then top quark, which people were always looking forward to have at that time, it really took a very long time. Finally, in proton and antiproton collision experiments at Fermilab, United States of America, top quark was observed, and it is really very heavy one. And then around 2000, Fermilab also established the neutrino partner of tau lepton. Then one typical particle, Higgs boson, which was proposed by Higgs in 1964 in order to provide mass to all the particles. This was formally observed at a Large Hadron Collider at CERN, Switzerland, and this happened around 2013. After that, some exotic particle, I will just name them, maybe I will talk about them later on. Pentaquark states and tetraquark states, which I preferably call exotic particle. They have also been observed at the Large Hadron Collider. It is still puzzling. Why should we have them? But of course, we have mechanism to accommodate these new guests. And around 2017, gravitational waves were observed from a pair, being emitted from a pair of black holes by Weiss, Thorne, and Barish. So, if you look at, in fact, so the list I have given you is only the major one. But if you look at the mesons, there are so many mesons, even this sheet is not actually complete. You can call it a particle Jew. But there are few things which you can note down. That look at the very first entry in the first column, 5 plus. So here you find numbers given as 1 minus 0 minus, or say with 1 minus 0 minus plus. We need to understand them because first one is corresponding to isospin, and 0 is the value of their spin, that is J, and minus associated with 0 as a subscript, and minus plus, they are ordinary parity and charge conjugation parity. In fact, these quantum numbers are required because they are common with a particular family. And with I power G, that is, it's not actually power; it is just a superscript. So minus is corresponding to their G parity. But I won't go into the technicalities of these at the moment. I just want to give you that there are a large number of mesons which are light, unflavored, strange one, charmed one, and bottom ones, even neutral charm, neutral bomb, strange numbers, and so on. And the list is not complete. I just gave it here to show you how things are there, and you don't have to remember them unless you want to do particle physics. The similar Jew is also available for the baryons. So if you look at them, let me see what is the highest value of total spin I have here. It seems to have three, but I think four and five spin value particles have also been, yeah, four is already there. So four and five spin values have also been observed for meson. In in the case of baryon, you see that the proton seem to carry half, spin half, and plus parity. Same is true for the neutron. So if we have many heavy bundles of proton and neutron given below, and then we have sigmas, lambdas, xi's, and charmed baryons, bottom baryons. Again, this list is not complete; it is broken. I have given it just to show you. So several hundred mesons and baryon have been detected. So this indicates there must be some kind of a structure lying behind them. So if my number is all right, over 200 particles have been discovered. By the way, you can always go to the particle data group site. It is free, and you can always find out more and more details of these particles from there if you're interested. But incidentally, these baryons, the baryons and mesons which I have just given you, most of them are not fundamental. Actually, all of them, if you consider all mesons and all baryons, are not fundamental, whereas leptons are. And most of them are also unstable. They decay immediately. In fact, most of them decay within a very short lifetime, which is of the order of strong interaction lifetime. That means 10 to power minus 24 seconds or so. By the way, how do we name this particle? They are named with letters from Greek and Roman alphabet. You could have also chosen Sanskrit letters, but presently it is a tradition to choose these names from Greek and Roman one. And don't feel discouraged if you have trouble remembering them. Even Fermi once said to his student, Lederman, who also got the Nobel Prize later on, young man, if I could remember the names of these particles, I would have been a botanist. So, don't worry, we can always have these tables with us and can do it. So we first have to remember how do we write these particles? What are the characteristics, properties of these particles? So see that each particle has a mass. Certain mass is associated with them. Very rarely photon-like particles don't have mass, but most of the other particles, particularly the matter particle, they carry mass. In the beginning, people thought that neutrino may be massless, but even though those neutrinos have a very little mass associated with them, and it is one of the important problem of modern days to understand the spectra, mass mass spectra of the neutrino. Then each particle carry definite spin. Incidentally, those who have studied symmetries may remind that when you combine Lorentz transformation with space-time translations, you end up with having a Poincare group, Poincare transformation, and it is a consequence of Poincare invariance that every quantum state must be specified by at least two things, that is mass and the spin. But these particles also carry parity behavior, and typically C parity behavior also. And then besides that, they have another set of quantum numbers, as I mentioned yesterday also. We have plethora of quantum numbers to designate these states, and we have to live with them. The first category is baryon number, lepton number, which probably mostly are familiar. Then we have heard about isospin given to us by Heisenberg to understand the near degeneracy of neutron and proton. But then strangeness and charm and bottom and these fancy words came to make life comfortable, at least verbally, though it require a typical mathematical treatment and using group theories, symmetries, and more formally, we have to develop relativistic quantum field theories to understand them properly. But besides that, there are other quantum number like colors, which we will see is coming soon. This is what is happening in this world of particle physics. And then so many large number of particles we see, we can classify them comfortably so that the load over our mind is highly reduced. I put them in three category. One is a non-exotic particle, which are very welcome member, and we understand them comfortably well using standard model. Then there are exotic particle, as I mentioned. Even though theoretically people expected there are tetraquark, because probably you know it already that baryons are made up of three quarks. So tetraquark states, pentaquark states, hexaquark states are also been seen at CERN. Yeah, though theoretically we expected that maybe they can exist, but we were not sure. But now we have experimental evidence for them. A third category is not much important at this stage, but I should have included them here just to remind you that life is not finished with these non-exotic and exotic particles. There are a large number of hypothetical particles proposed for several theoretical reasons, like CP violation, dark matter candidates, supersymmetric partner of these quarks, leptons, and bosons, boson quantas. But then, as you unify all the interactions, we require more and more quanta to establish granular fat theories, and maybe there is another layer of quarks and lepton, as Harari proposed the existence of tau and Wohus prion substructure, and maybe many more. All of you can think of some new kind of particle, because unless somebody contradicts them, all those predictions and suggestions are actually welcome. Now, coming back, I will focus mainly on non-exotic particle. These are three. They put in three or four category. One is leptons, the other is hadron, third is quanta, and Higgs belong to its own class. So, if you understand the atomic structure, then life is not difficult, because all leptons are quite electron-like. So, if you understand the behavior of electron, you more or less understand the behavior of all the leptons. Similarly, hadrons are, they have two classes within them. There is baryon and mesons. All baryons you can think of nucleon-like, or like heavy brother of neutron and, and proton. Whereas mesons can be thought of as pion-like, so they are like heavy brother of pions and so on. So if you understand pion and nucleon, then life is not difficult for baryons and mesons for you. And all quantas, that is photon, W's, and gluons, their behavior is quite quite similar to photon. And you know that photon is basically described by quantum electrodynamics, which is nothing but quantum version of Maxwellian classical electrodynamics. And there, the charged particle, like electrons, behave as the source of the electromagnetic field. In the same way, these electron and quarks ultimately they act as sources of all 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 force quanta. So they interact with each other through exchange of the quanta, which I have given you in the very first sheet. So one can comfortably keep focused on lepton, hadron, and quanta. Then we can say that we have done justice to the topic. So with this, we come to the first family, that is family of leptons. This is a Greek name just meaning light, even though this meaning is now useless. So we stuck with the word lepton and we define it differently. Today we define leptons are those particles which do not participate in strong interactions. So they participate only in electromagnetic and weak interactions. And as I've shown you before, that electron was the first lepton or first fundamental particle. It is the lightest fermion which seems to be stable. Because if electron is not stable, then charge conservation has to be in, in danger. And its neutrino partner, as we have already discussed, was predicted by Pauli in 1932, observed around 1950. Until 1975, there were only four leptons, that is electron and muon, with their partner, neutrino partner, electron type neutrino and muon type type neutrino. Here, E and mu are charged particles, whereas neutrinos are neutral. Then in 1975, fifth electron was observed, which is named tau, and its mass is 3,500 times the mass of the electron. So roughly twice the mass of the proton. So this is how this electron, meaning light, cannot be held seriously today. And this tau lepton also has a partner. So this is how we have six leptons: electron, muon, and tau with their corresponding neutrino partners. And all these six leptons have their anti-lepton partner. So for electron, we have positron. For a neutrino, we have anti-neutrino. For mu minus, we have mu plus. And for muon neutrino, we have anti-muon neutrino. And tau minus was observed first, so we have tau plus also. So in this way, family is complete, and their various properties are given in this table. So all the six leptons are given in the first column. Their mass is given in the next column. So electron is the lightest fermion and lightest massive particle with mass 0.51 MeV, and muon mass is roughly 5 MeV, almost 200 times heavier than the electron. And tau, as I mentioned, is around 3,500 times the mass of the electron. And out of these, then we have their neutrino partner. I have mentioned here stable, stable, stable. You have to be a bit careful about it. Electron is certainly stable to the best of our knowledge. Muon and tau, its charge partner, heavy, heavy electrons, they are certainly not stable. The muon decays to electron with a pair of neutrinos. Similarly, tau also decays to mu. Tau can also decay to electron, but it prefers to decay to muon through weak interactions. However, when you look at neutrinos, electron type neutrino, muon type neutrino, tau type neutrino, I have put column stable. The stable is with a pinch of salt. because very recently, in last I think maybe decade or so, and Japanese collaboration people have established the so-called neutrino oscillations, and we required those kind of oscillation in order to understand a neutrino emission coming from sun, because the number of expected neutrino was double than what was observed. And people, theoretical people, suggested that maybe on the way they change one into another. So this is called the neutrino oscillation, and it was established experimentally by Japanese group. And by the way, here we have already seen the charge that electron, muon, and tau are charged with -1, and they have antipartners with charge +1. And all of them carry spin half. H, of course, H is the unit of this. And I think everybody knows that if spin is half, then its third component is also there, that is plus half and minus half, giving orientation to the spin. But last part is important. Sometimes books say they all carry lepton number 1. No, we have to be careful. We have three kind of lepton numbers: electron type, muon type, and tau type. So you can call it electron lepton number, muon lepton number, tau lepton number. So the first family, that is E and nu, E, they have electron and lepton number -1, and all other lepton number 0. And if you ask me the lepton number of positron and its partner and antineutrino, that will be +1. So when you go from particle to antiparticle, many of these quantum number change sign. Charge will change sign, lepton number will also change sign. Mass would be same. So similarly, muon and its electron partner nu mu, they have muon lepton number -1 and other lepton number zeros. So tau and nu tau also have a new lepton number, tau lepton number -1, and electron lepton number and muon lepton number of tau and its partner is 0. So in any reaction, as I mentioned in the very first talk, symmetries are very important to understand everything which be happening around. But when we see our teaching and learning, we find they are taught right at the end. Whereas to me, they are right in the beginning. They control everything. For example, here, wherever you have lepton processes in which electrons participate, then these quantum numbers have to be honored. Uh, at this moment, I can say that a lepton number in any process must be conserved. So not only the total number of electrons, but also the electron type, muon type, and tau type lepton number should separately be conserved. So this helps us a great deal in looking at various decays. Maybe I will spend some time on that later on, because today I'm just giving you overview of these particles. So with this we come to hadron. Hadrons are a bit strange. In Greek it means heavy. So there are a couple of hadrons created, and as I have already shown you the list, baryons with spin half, spin 3/2, spin 5/2, up to 13/2 have been seen. To the best of my knowledge, every day sometimes come new surprise. In the meson family, we have observed mesons with spin 0 like pions, spin 1, spin 2, spin 3, spin 4. By the way, this, when I say spin, it is total spin, because we observed it at a spin. However, this spin may be arising from addition of quark spins with their orbital angular momentum. It's just like hydrogen atom. You know, when we study hydrogen atom spectroscopy, electrons carry many kind of angular momentum, many kind of quantum numbers, like principal quantum number n, orbital quantum number L, and azimuthal quantum number, that is magnetic quantum number, and also the spin quantum number. And it is the addition of orbital angular momentum with the spin of the electron that gave rise to the total angular momentum J as L plus S, and you know that L plus has add 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 vectorially a proper understanding of addition of angular momentum and spin require angular momentum algebra. I suppose everybody has here. Anyhow, these baryons and mesons, even though they are over several hundred, but most of the hadron decay quickly, living around only a very small fraction, 10 to the minus 23 second, which is called typical scale of strong interaction. By the way, it is not difficult to remember this number because it is the time taken by light to cross a actual proton. You know, proton size is around Fermi, and if you divide it by speed of light, you get this idea. So all heavy states, I mean, for the moment you keep spin half baryon and spin zero meson separate. So all heavy spin particles, that is spin 3 by 2, spin 5 by 2, 7 by 2, 9 by 2, 11 by 2, 13 by 2, all decay to lower states, preferably ultimately settling around decaying to protons and neutrons or their heavy partners, spin half ones through strong interaction, because they are just in a way, if you like, I can talk about that here. In a way, you can think of them as excited state of three quarks. So as you know, that excited state of electron in hydrogen atom decays down to like low energy state. Similar phenomena is occurring here. So this is one way evidence for some kind of inner structure of baryon. In the same way, mesons also. Spin 1 particle, spin 2, spin 3, spin 4, they decay strongly. Again, having a lifetime of the order of 10 to minus 23 second. If for some reason, say energy conservation, some decay is forbidden to occur through strong interaction, then it looks for electromagnetic processes to decay. Sometimes we also observe electromagnetic decay, which most of the time emit a photon. When a heavy baryon, for example, delta plus is a heavy baryon, which you'll see, it can decay to proton with the emission of photon, which is an electromagnetic process. Because wherever you see photon, it is an immediate signature of electromagnetic force, and wherever you see neutrino, it is the immediate signature of weak force. So in this way, you can see that spin half baryon and spin zero mesons, they don't have sufficient mass to decay through strong interaction. So then they prefer to decay to lower energy states, either weakly or or electromagnetically. Incidentally, when these so many particles were found at that time, lots of job was done by experimentalists. People were really getting result. So they were trying to find out pattern among them. So in that finding out pattern, Gallman and Kishijima, they found ultimately that baryons carrying fixed spin and fixed parity, they seem to appear in a group of 8 and 10. By the way, this is the story of 1960s, because now we have much more, many more actually baryon. So fixing time around 1960s, we find most of the baryons family, that is, they may have any spin, but once you fix the spin and of course parity, then number of baryons observed are falling in a group of either 8 or 10. Similarly, mesons they were seen to form octet pattern or sometimes octet and and singlet together. So this interesting pattern 8 and 10, particularly 8, inspired Gell-Mann to propose a typical symmetry, which is named as eightfold way, or formally we will call it a special unitary group in three dimension. By the way, before I touch that topic, let me introduce why do we need strange particle and why do we need this strange quark or strange quantum number. Because isospin was already introduced by Heisenberg, and is again a textbook material everybody studied in nuclear physics book. So, of course, as I mentioned, that most of the information on particle physics has come from scattering experiments. So suppose you collide one particle with another with sufficient energy, they end up producing even states heavier than them. For example, here when pi meson was collided with with proton, it's pi minus. So overall combination is neutral. Around 1947 and 55, K mesons and hyperon were observed in such processes. So they kept on increasing the energy of pi. And if we have sufficient energy of ion, it can produce lambda particle and K0 particle. This name came later, but now we know that lambda and K0 are produced. Lambda this mass, if I recall, nucleon mass is around 940 MeV and lambda mass is 1115 MeV. Kn mass is 490 MeV, where pion mass is 140 MeV. So this lambda, the moment it is produced, it decay to neutron and pi zero. It can also decay to proton and pi minus, whereas k zero decay to pi plus pi minus. So by the way, because lambda and k are produced, but they immediately decay. So if you imagine a process occurring, is what we are saying is pi minus colliding with p in a reaction. Probably this experiment was seen in this phenomenon was seen in cloud chambers experiment. Then what do they see? They see two V events, because you know that in uh, such a detector only charged particle can be seen through their tracks. So people call it V events, because lambda decay to proton and pi minus and K0 decaying to pi plus pi minus. So after they are produced, they continue living for some time. So we see two V events separately, but connected with the main target, that is P, through neutral particles. So this gap was measurable. Why this gap was measurable? Because lambda and K0 have relatively longer lifetime. When I say longer lifetime, because it's lifetime of the order of 10 to the minus 10 seconds. So for our scale, this is very, very small time, but in comparison to strong interaction lifetime scale 10 to the minus 23, they lived 10 to the power 13 times longer than the lifetime scale. So this behavior was puzzling behavior. It is a strange behavior. In the sense, lambda and k were produced through strong interaction, that is between pi and p, but decayed through weak interaction, lifetime 10 to the minus 10 second. In order to understand this behavior, Gell-Mann proposed to introduce a new quantum number that is called strangeness. He says this quantum number strangeness is such that it is conserved in their production reaction. However, when they are decaying, then it is not conserved. You can go back to the process and look at it again. Suppose lambda carry a strangeness minus 1 and K0 carry a strangeness plus 1. Obviously, strangeness is not carried by a pi and a proton, because both are the already seen particle. So you see that pi minus and p have zero strangeness, lambda has minus 1, k0 has plus 1. So in their production mechanism, strangeness is conserved. But when lambda is decaying to p and pi minus, or n and pi 0, or k0 is also decaying to pi plus pi minus, they are decaying to non-strange particles. So that is why in their decay process, strangeness is not conserved. I am spending time on this sheet, making you aware of this, that these quantum numbers, not all of them are conserved. We will see slowly that in strong interaction, most of the quantum numbers are conserved. The electromagnetic process is total isospin can be violated at the maximum by 1. That means total isospin of final state and initial state may not be same, whereas third component will be conserved. However, weak interactions are notorious. They are well known to violate as many quantum numbers as possible. So they violate maximum number of conservation laws associated with these things. And people believe that even new kind of weak interactions can be there, which will violate probably even the bearer number and lepton numbers, which are supposed to be honored in strong electromagnetic and even in so far seen weak decays. By the way, there is a connection also between these strangeness quantum number. You know, in nuclear physics, we have studied the charge of nucleon is connected with the third component of isospin and with the barrier number, that is nuclear number. So when you include the strange particle, one can extend the Gell-Mann and Nishijima formula from Q equal to I3 plus B by 2 to this one, which I am showing here. So this B plus S sometimes also known as hypercharge. So that is how these strange particles came on the scene. And with this, we find, for example, the meson family. Here I am giving the introduction to pseudoscalar particle and vector meson. Why do call them pseudoscalar particle? Because their spin is zero, so their behavior is like a scalar object. But scalar object is usually supposed to have a positive parity behavior, whereas these particles have negative parity. So JP state is 0 minus, so we call them pseudoscalar. Whereas vector mesons, vector means spin 1, like photon, but this is not photon here. These are just like photon because they have same spin 1. And natural parity for vector is minus. Do we have particle with 1 plus, that is positive parity? Yes. We call them axial vectors, but I'm not actually referring to them. But there's an interesting thing. If you look at pseudoscalar family, that means 0 minus family and vector family, they have nice correspondence. So let us focus first on the octet of pseudoscalar particle. We have K plus K0. Then we have pi plus, pi 0, pi minus. Of course, historically, pines were observed before and were also proposed before. And then we have K0 bar and K minus, and of course, a single state eta. Why I have grouped them in this way? Of course, first of all, these first 8 particles form together because all of these particles have spin 0 and minus parity. So they come in one set. And K plus K0, if you look at isospin, their charge is obvious +1 and 0, but they form iso doublet. It is something like proton and actually neutron. So they have isospin half, and their third component plus half and minus half goes with K plus and K0 respectively. And they have strangeness +1. And so if you add their barrier number, because barrier number of all the meson are 0, their hypercharge Y, that is B plus S. So it is not a new quantum number. If you like, you can continue with with the strangeness, but because books talk about hypercharge, I just added here in this table. Hypercharge Y is nothing but sum of barrier number and strangeness. And since barrier number of all the meson is always 0, so hypercharge and strangeness carry the same value. So coming to the next, that is pi plus, pi 0, pi minus, we already know from Yukawa that they form isotriplet. They are isovector or formally isospin 1. And you know that whenever we have entanglement spins, isospins, we have a third component associated with them. So their charge is plus 0, minus 1 respectively. And they have third component +1, 0, -1 of isovector, that is total isospin is 1. And they are not strange particle, as I mentioned in the last slide. Then we have sixth particle eta, which is charge 0, neutral member, and its isospin is also 0, so it is called isoscalar. So sometimes we use formal language, isospanners, isovectors, isoscalars, so we have to live with this kind of terminology. So it also has zero strangeness. Then we have K0 bar, K minus. Why I put a bar? Because I want to distinguish between K0 and its antiparticle. Why? Because just look at their charges are zero, but look at their strangeness. Strangeness of K0 is +1. You can see it here. And K0 bar has a strangeness -1. So they are not the same actually particle. They are different particle. K0 bar physics is one of the interesting area which has important connection with CP evaluation, but that is a topic of some other talk, some other day. So K minus is obviously the antiparticle of K plus. So this number 7 and 8 particle which I am seeing here, they are antiparticle of this, whereas antiparticle of pi plus is right away minus. And what about pi 0? You can call pi 0 is antiparticle of itself. And then we also find a singlet meson eta, which is like a heavy brother of eta. Its mass is around 958 MeV, and charge 0, isospin 0, and strangeness 0, and obviously hypercharge also 0. So see again that if you look at K plus K0 and look at K minus K0 bar, their mass is clubbed around 495 MeV. It is quite similar to pi plus pi 0 pi minus, whose mass is around 140 MeV. That is why I have put a little space between them, as if it is an iso doublet and iso triplet and iso singlet, iso doublet and iso singlet again, because all of them are coming with the spin 0 and minus parity. We are putting them in a group of 8 and 10. So this is called octet and singlet. Correspondingly, we have a vector meson family, that is spin 1 and parity minus. So we have heavy partner of K plus to K star plus. So star is added just to actually remind us that they are quite similar to K, but still they are different. They are heavy and they carry different spin. But their internal quantum number like charge, isospin, strangeness, they share it with K plus K. In fact, in this will happen in all the meson families. So if you go to spin 2 meson or axial vector meson or even more heavy mesons, all of them will have something like K's and something like pi's and something like K's, anti-K's and so on and so forth. So their description of isospin and this strangeness quantum number will not change. So what will change? Their spin will change, their parity may change, and their, of course, masses will change. And obviously, we need to have different name. Even people are tired of finding out a new name. So we are in the habit of sometimes giving different name. For example, for pi, we have row partner, but when it comes to K, B, we simply put star. So sometimes what do? We just add K and write their spin within the bracket. So if you look at the particle group literature from internet, one can see these things easily. So this completes a brief introduction of Meson's family. Of course, this Meson family was observed. So if you like, you can draw a diagram that is I3 on the horizontal axis, that is third component of isospin, and strangeness or hypercharge on the vertical axis, because both I3 and S are discrete. They are like quantum number, so they have discrete values. So if you plot them, it is a small.
Sir, maybe we can take a break here and then continue tomorrow, sir.
Yeah, one or two sheets more. That is all.
Sure. Okay, sir.
So in this way, and these particular diagram which reveal the octet and octet are known as weight diagrams. So in this way, we have a similar diagram for vector mesons. The list of the particle I have given before. One can take it as a homework to draw. But when we come to the baryon family, we have octet of baryons, which is made up of proton, neutron, lambda, sigma plus, sigma 0, sigma minus, xi 0, xi minus. Sometimes we also call them cascade particles. So here we again see something similar pattern to meson octet. We have one iso doublet, one isoscalar, and then one iso triplet, and then second iso doublet. Their mass are quite close by within one particular multiplet. So only charges differ. But and of course here I have given their charges. It's a small exercise for my young friends to see them. And then isospins, and we have to be bit careful about isospin behavior of proton, neutron, and these deltas. Whereas here we have some kind of similarity, because both sigma and sigma star, which belong to a 3 by 2 spin, they are isovector, and they also carry active properties similar to mesons, with one difference. Here we have strangeness -1, so hypercharge come out to be 0, like the meson family. And xi particle have isospin plus, have minus half, and new things are coming here. They carry more strangeness, that is -2. And similarly, when we go to 3 by 2, we have similarities here, but there is a typical difference here. In place of having iso doublet, here we have iso quartet. So it means their isospin is also 3 by 2. Their spin is also 3 by 2, and their isospin is also 3 by 2. I will talk about isospin more actually in more detail maybe tomorrow. But still, one can easily connect, because this is a textbook material, at least in the nuclear physics nowadays. So hopefully our young friends have done that in BSc. But the beauty is, around 1962, only 9 of them were known experimentally. And this omega minus was, in fact, one of the grand prediction of theory, by, which was made by Gell-Mann around 1962, where he could find a right kind of a grouping as a generalization of isospin group to explain octet and decoupled pattern of baryon. Since at that time omega was not seen, he not only predicted its charge, and he also gave its mass. And within a year or so, experiments were done. Omega was discovered to lie at this mass, which is quite consistent with Gell-Mann prediction. So that brought us a great faith in internal symmetry groups, which we are studying. And similar to meson, we can draw these octet and decoupled pattern for baryons using the same kind of a thing. It is I3S plot. This is plus half and minus half, plus 1 0 minus 1, as for E3, plus half for the proton, minus half for the neutron. And steadiness is 0 for this line particle, and -1 for this, and -2 for this. So you can take it as a homework. So similarly, decoupled, we have quartet, that means spin, isospin 3 by 2. All these 10 particles have spin 3 by 2. So on the vertical scale, these are non-strange particles, that means steadiness is 0. There is -1 steadiness with sigma star family, -2 steadiness here, and omega here. Because as I mentioned, omega was not seen, so it was a trivial work for him to find out the properties of that. Because interestingly, they also follow equal mass difference formula, that is mass difference of sigma star and delta is quite close to mass difference of psi star and this sigma star family. So he could guess the mass of omega very well. So I think maybe let me see what is the next, and then I'll probably stop. Yeah. So this is going to be the real focus of tomorrow. I'm thankful to Professor Shastri. He asked me to introduce symmetric groups a little more formally. As I have been mentioning from the beginning, that symmetries are not really paid that much attention which they deserve from the beginning. And to tell you the truth, in fact, I find everywhere, even in classical physics, physics is really nothing but a description of, of, of symmetries. And we find these symmetries to be responsible for three things. One is the degeneracy, that means the near energy value of a particular multiplet like proton or a neutron. And these symmetries are also responsible for conservation laws, both kind, external as well as internal. But ultimately, that is a real beauty that dynamics is dictated by the symmetry, and that we seen through gauge invariance as an example of that. So maybe I can stop at this point, and I will continue with this sheet tomorrow. Okay, Shastri.
Yes, sir. Thank you, sir. Thank you very much. I think this is the right place to stop. And yeah, tomorrow we can start with the role of symmetry. It will be wonderful. Yeah, because these are, not, as you said, not very well covered in our,
Yes,
focus is not given, enough focus is not given on this.
they are
There
there.
should be an emphasis on this. Yeah, they are there, but emphasis should be there on this.
Sure.
Thank you, sir. Thank you very much. So again, we will meet tomorrow at 4 o'clock. And I think from there we will take it forward. Thank you, sir. So I'm closing this meeting.